and now, like I said, I'd like to ask you a bunch of random questions.
Sure.
Okay, so it's plenty of time. So instead, I'll ask, just random, random questions. Like I said, random questions. First one, obviously, is what we talked about at the very beginning before we started recording, which was just um, what's your background? Because your background was very interesting. Um,
Mm.
but you start. I guess you started out. You said with Bekenstein.
Yes.
Okay, so uh, could you explain how you got where you are today?
So yeah, I mean, I did my PhD in Jerusalem under the supervision of Jacob Bekenstein, who passed away in the last, I think, 5 years ago, something like that. And Bekenstein worked on black hole physics. There is a very well-known relation between black holes and entropy that are called the Bekenstein-Hawking entropy, because Bekenstein found that the entropy of a black hole is proportional to the surface of the horizon area. The event horizon of the black hole has an area, and that area is proportional, the entropy of a black hole proportional to that area. And Hawking found that the black hole emits radiation known as the thermal radiation. And this radiation has a temperature that and it corresponds to an entropy that's proportional to quarter of the area. So essentially, Hawking found the factor quarter that goes to the formula of the black hole entropy. All the units I'm using are units that used a lot in general relativity, where you take the Planck constant to be 1, the h bar to be 1, and everything is 1, all the constants. So it's dimensionless units. But of course, you can plug into the units to get to the precise. But it's in dimensionless units, it's a quarter of the area. Yeah, so since then, Bekenstein approach to quantum gravity, because we don't have theory of gravity, of quantum gravity. So his approach was following something like Ehrenfest used for quantum mechanics, where before there was, we used to have this old quantum mechanics formalism where people didn't have the full theory, but they talked about principles of quantum mechanics and got ideas on how the theory should be. And Bekenstein tried to apply this to quantum gravity and the work of black hole physics, and worked on trying to quantize the surface area of a black hole. And so he had a lot of work on this. So that's what I worked for my PhD. And also a little bit of my first postdoc in Edmonton under Valerie Folov. And then after that, I fell in love with quantum information, with the theory that has a lot, that the theory itself is strongly well known, but still its implications and applications are still quite far from being fully understood. So I found it fascinating to have a theory that really you don't need to make an assumption about, because every model in quantum gravity starts with certain assumptions that you have to accept, and that's why we have different groups of quantum gravity. Some talking about, quantum loop gravity, string theory, M theory. All those, you have even causal sets that they describe, or there are different models of gravity out there. Yeah, I mean, it's like, I personally never knew which model is the correct one, which one I want to put my emphasis. So I decided to change my field to something where I can at least know that the theory I'm working with is very sound, and it's simply quantum mechanics. So that's how I got into quantum information, and then quantum resource theories from there.
Okay. Okay, so how do you, should be a simple question. How do you approach your research? What how do you get ideas? How do you once you have an idea, how do you flesh it out? Is there any are there any regularities that you notice about yourself?
Oh, yeah. I noticed that I have questions about fundamental. I'm interested in foundations and fundamental questions. For example, to me, a concept that known as uncertainty puzzled me, and trying to understand what do we mean by uncertainty, what do we mean by entropy, basic, very, very basic questions like that really driven my interest in finding a problem. So there was a time where I was very fascinated what uncertainty is and start studying it and learn about, and as a result, developed the uncertainty principle with a quantity known as majorization in a more fine-grained version of the uncertainty principle, where we deal with the probabilities rather than just with certain particular quantities like variance or entropies. And this all came from just a simple interest in what uncertainty is. What do we mean by that? And I started thinking about dice and going to gambling games. And so then I discovered, oh, I can actually model a lot of things using gambling games. And then from there, I studied and learned a lot about about the uncertainty principle, which is very interesting to me because I strongly believe that, if you go, you never know what you're going to discover. You cannot impose on physics. That's the beauty of it. You can't impose what you want. You can bring your agenda to your research. Like sometimes we start research and we want to calculate this and get this result and then show that. And sometimes the road goes a different way than what you expect because new problems comes up. You discover that your original agenda is totally not relevant, and you have to accept what nature gives us or what the mathematical structures impose on us. And this kind of an humble approach, open approach, to be open, see whenever, to just totally see what is there and just feel like this knowing that going in this particular direction. Because I liked a lot of times I tell my students sometimes that I like to think about it as the bird, before it's kind of like jump into the water. And, when I was in San Diego, I did my postdoc there, I saw it actually, how birds in the ocean, they make these circles before they kind of like jump into and take their prey. And I always like this imagination because a lot of times when we do research, we right away jump into the problem without doing that circle a little bit before putting all the energy and all the thought. Just think about, this is the right direction that you want to put your energy into, and then jump into the water and try to get to solve the problem. So yeah, that's kind of my view of this.
Okay, excellent. Okay, so this one's a quiz. Can you qualitatively describe the differences between the Helmholtz, the Gibbs, and the Helmholtz free energy, the Gibbs free energy, and the enthalpy? What would you use them for? Not so much, the statistical differences, but what can you do that? I mean briefly.
Yeah. So entropy is a big topic. I will just say that entropy is, to me, my understanding of entropy, because a lot of time people associate, I just spoke about uncertainty, actually it's quite relevant because entropy is a sort of a measure of uncertainty. So entropy so entropy is uncertainty, is also a measure of uncertainty, but or disorder, right? That's how we sometimes like to say it, but it really represents our uncertainty about the system. That's why the system is disordered. And it represents also, it's an additive quantity where that it's increased additively. If I take two systems together, then the entropy just increased by doubling and not by something else. And that's how it's a bit different than uncertainty. Uncertainty is a bit more general, doesn't have to be additive, but entropy has to be additive. And the Gibbs state is basically, so we spoke, what you said, the free energy, yeah. So the free energy is essentially like the energy that can be used. That's why we call it the free energy that can be used to get work from the system. And now in thermodynamics, sometimes people using batteries analogy for the Gibbs. So certain it's like the free energy is like measure the battery. So for example, the free energy of the Gibbs state is 0. Because the Gibbs state, even though it has energy, in fact, it's diagonal in the energy eigenbasis, but it has a 0 energy, free energy, because you cannot use it for anything useful thermodynamically speaking. So if I think about it in a thermodynamical concept, it cannot do. How it is related to entropy, it has definitely it has non-zero entropy. I would say that it's the state that minimize the entropy for a given energy. Let's say, did I say it correctly? So the Gibbs state minimizes the entropy for a given energy. If we have a certain energy, the Gibbs state would be the one that minimizes the entropy as the least amount of entropy for that given energy. Yeah.
Excellent. Wonderful. I shouldn't say nobody. You understand those things, but that's the hardest thing when you take your freshman thermodynamics classes. They send you out, they send all these quantities at you, and you have no idea when to use which or whatever, and that's
right. This is the thing about thermodynamics, and I think we are still in a position with thermodynamics that we still don't know how useful, like when you study thermodynamics, you don't study it from the bottom up. It's not like a theory that you study from the beginning, starting with certain axiom and build it up. It's more like from the top up down. So I think what we're trying to do with resource theory is really write thermodynamics, develop it from the bottom up, starting with the very, very basic principles, even explaining why the Gibbs state is the free state of the system, even that, why we consider it the thing that is most useless in terms of resources. Even that is not fully understood, at least not to me, from a very fundamental point of view. I mean, I understand that it's the only state out there. There is something known as passivity, and people study in thermodynamics passive states, and the Gibbs state is the only passive state that I mean, people can Google it, what is passive states, and see that the Gibbs state has a unique properties in terms of that passivity. But so that was an attempt done by the community to even motivate further the Gibbs state, but it's still not it's not like in entanglement theory that I can understand why the maximal entangled state is so useful. So or why the product state is really the free state, because there is no entanglement in product state. So here I don't exactly, starting the problem without knowing anything about entropy energy, starting it from the bottom up. That's my goal in thermodynamics, and I hope one day we will have the full theory well defined.
Okay, excellent. One last question based on your gambling interest.
Yeah.
I probably shouldn't say it that way, but I don't know. You know Ian Hacking, right? Have you read The Emergency of Probability by Ian Hacking?
I heard about it. I didn't read about it.
Okay, so this book, when I read it, had a really interesting description, and it was talking about Leibniz trying to figure out the probabilities for a pair of dice. Okay.
Yes.
And it turns out that he had decided not to do it the correct way. What he decided, instead of counting each dice as independent, he decided that rolling, let's pretend you have a red and a blue die. He decided that rolling the blue 1 and red 5 is equivalent to rolling the blue 5 and the red 1. And he counted those up. And the way Hacking described it was Leibniz had pretended that the dice were bosons, right? Because basically that's how that works. So when you were doing all that thinking about probability or gambling and probability and things like that, do you have a game that would be described by one of those probability distributions?
Right. The game is this. I can give you a game, and it comes to partial orders actually, and this partial order is called majorization mathematically. It's a topic that actually in matrix analysis has been studied for quite some time. There is a book called Majorization by Marshall and Olkin on just devoted to that. And other books on matrix analysis also contain majorization. So it's a topic well known, but I'm not sure how much it was well known that it's connected to actually gambling game. So suppose that you take a dice, and suppose that I want to understand, when I look at the dice, I want to understand what is, how much, suppose the dice is biased. You see, instead of thinking about dice as being unbiased, that's what suppose it's a bit inhomogeneous, right? And so now suppose you have two dices and both of them are non-homogeneous, okay? How would you know which one is more uncertain than the other, right? Which one you would choose if you played a game of chance and you had to guess what would be the outcome? Which one of them would you choose? And so let's think about a game. It's a very, very simple game where you just have to guess what's the outcome of the dice. But suppose you know the statistics of the dice. So you know the two probability, the red and blue dice. You know what's the probability for 1 to occur, for 2 to occur of the blue one. And then you know, again, the same thing for the dice, the red one. You know the red 1, the red 2, the red 3, the probabilities of those chances to occur. How would you know which dice to pick if all you had to do is to guess what's the outcome? So you go to the casino and you roll the dice, and your job is just to guess what's the outcome. If you guess it correct, you win. Of course, you will, because you are given the statistics, the probabilities, you would look, what's the probability for 1 to occur? What's the probability of 2 to occur? And you would choose, and you will guess. So there are two things. One is what you will guess, and second, which dice you would choose, right? So suppose you chose the blue one. If you chose the blue one, which number you will guess? You will guess the number that has the highest probability to occur. If it was a natural, if it was an unbiased dice, all of them are equal, so it doesn't really matter. But if it's biased, there might be a probability that number 1 maybe has the highest probability to occur, just because of the unhomogeneous nature of the material making this dice. So so you would choose maybe the number 1, or so you would choose the number with the highest probability. And which among the two dice, you will choose which among those two dice has a number with the highest probability. So you will choose, you will look what's the highest probability for a particular number of the blue dice to occur and which one in the red dice to occur, and you will choose the one that has the highest probability, right? So suppose the blue dice has a probability 1/3 that the number 2 occur, and that's the highest, and the red one has the number 3 occur with the highest probability is a quarter, so you will take the blue one because it has a third, 1/3 of the times the number 2 occurs, so you'll choose the blue one because it's the highest probability. But now think about this. Suppose you change the game and you say, now you have to guess two numbers. Like you're rolling the dice, whatever dice that you'll choose, you'll roll it twice. You're rolling it twice, and you have to provide. You are allowed. Sorry, you're still rolling it one, but suppose you are allowed to provide two guesses. That's what I'm trying to say. So suppose you are allowed to provide two guesses. You don't have to provide only one guess, and you're still going to win if one of them occur. This could be, of course, with dice, when there's only 6 options, that's maybe too much, you know, the host giving you a chance to win too high. Nobody will give you that high in a casino. But suppose there are dices that have many options, right? Because it doesn't have to be a dice. It could be any physical system. It could be the roulette, right? So you can choose certain numbers and you say, at least one of them occur, I'm winning. And so which two numbers you would choose? You would choose again the two numbers such that the sum of the probability, which dice you would choose, of course, which two numbers you would choose, it always will be the two numbers with the highest probabilities. So the first one would be the one with the total highest, and the second one would be 1 second to it, right? In probability. But which one you would choose, the red or the blue? You will choose the one that, suppose that the sum of the two is bigger than the sum of the other two. So what it is, it's not enough that one is instead. So it could be that for one particular game you chose the blue one, and then in one particular game you chose the red one, but for another game, if you are allowed to put 2 guesses or 3 guesses or 4 guesses, it will be another dice. So what you get is a partial order. That partial order among probability distributions. And this partial order among probability distribution is exactly what is known as majorization. And it's exactly what appears in uncertainty principle, in entropy. All entropy functions apparently monotonic under this partial order. So there are lots of entropy functions out there. They all monotonic under this. In fact, if they are not, then they are not really measures of uncertainty, because entropy measures the uncertainty of a system. And it's all come to this discussion of games of chance. That's the...
Okay, excellent. Well, that I think is perfect. I think everybody's going to want to, you know, come listen to the show now. That was great. I liked it very much. And I'd like to just thank you one more time for coming on. And
no problem. Thank you.